Okay, good morning, everyone. Hope you're all well and continuing to be successful in your semester. We have reached the end of our theme on the history of evolutionary robotics. We're going to finish that up today with Lecture 12, looking at one of the unique capabilities of the human species, which is bipedal locomotion. And then we'll move into another section in the course, which is sort of moving from the past to the future. What are some of the open challenges in the field of evolutionary robotics? We're going to look at a number of challenges. Along the way, I will point out that several of these challenges are challenges not just within evolutionary robotics, but in the larger landscape of robotics and AI as well. I mentioned at the beginning of the semester, one of the reasons why I think robotics and AI is so fascinating is that it's very much in its infancy. We have, you probably figured out by now, we have very little, we have a very loose grasp on what the foundations of intelligence are, how to define it, and how to instantiate it in machines. So should be fun. Okay, so back to bipedal locomotion. And again, before we talk about that, just a reminder, you're on assignment 8, which is implementing the hill climber, arguably the simplest search method next to random search you can imagine. One of you asked about about the behavior that we're evolving. I mention in here moving to the left and moving into the screen. So we all have exactly the same camera angle. We're looking at the robot from a diagonal angle. So the idea is that the robot is moving left. When it evolves to move, it should evolve to move to your left as you view the robot and look as if it's moving away from you in the virtual world. I think sometimes I say away from the observer or into the screen. Those all mean the same thing. Any other questions about assignment 8? I mentioned last time that I've already put up assignment 9 at least on Reddit. I haven't linked it into the schedule yet, which is where you'll be implementing a parallel hill climber. For those that finish up the hill climber early, feel free to start in on assignment 9. No, all good? Okay, so back to bipedal locomotion. I apologize for the copyright issues last time. Last time's video lecture is now up on YouTube without the Monty Python clip. We were looking at we ended last time by looking at two extreme examples of bipedal locomotion in machines that strike very different trade-offs between the 4 features of legged locomotion that matter to us. We looked at the Asimo robot, we looked at the passive dynamic walker last time, and then we ended by looking at the hybrid dynamic walker developed at TU Delft. In the Netherlands. This robot has an empty bucket on its head, which is sort of symbolic. It's meant to represent that this robot is extremely simple. There is no huge battery, there is no huge microprocessor, there is no complex orchestration of the legs. The bipedalism derives from the body of the robot, and then this robot gets literally and figuratively a small push. There is a small pulse of torque that is applied to the stance leg when the stance leg is behind the robot to kick it a little bit forward. That motor then turns off and allows the leg to swing forward like a passive pendulum, like our legs do when we walk at a leisurely pace. Okay, we ended by looking at some other sort of exotic examples of mechanical devices that also exhibit passive dynamic walking. Okay, so what we're going to do this morning is look at a research paper, and as always, I've assigned this for the reading for today. I don't expect you to read all of this or retain all the technical details. There are a lot of technical details in this paper. The authors packed a lot of information into 8 pages. I want you to again just focus on what was the aim of this project and what was sort of the overview of how they achieved it. So the research question the authors started with is, how can we evolve passive dynamic walking? I actually, when I was a postdoc, I worked in the lab next door to the lab at Cornell that was developing this passive dynamic walker. And whenever I'd walk by, they'd be in there with nail files and carefully shaving down the curvature of the feet. There was a huge amount of effort that went into fine-tuning the mechanics of this machine to get it to exhibit passive dynamic walking. A lot of human effort. As usual, in evolutionary robotics, we're lazy. Can we get evolution to do something that takes a lot of time and effort for a human to do? So what we're going to see in the first part of this experiment is the evolution of the body plan of a passive dynamic walker. You'll notice that there is a declined plane in this panel. They're going to put the robot at the top of the declined plane and allow it to do its thing. And if it falls over, it gets low fitness. If it happens to take one step, it gets a little bit more fitness. If it happens to take two steps, it happens to get a little bit more fitness, and so on and so forth. Unlike your assignment, where the evolutionary algorithm is evolving aspects of the neural network, or the brain of the robot, in this case, there is no brain. It's a purely mechanical device, and they're going to evolve instead parameters that describe the body. As you'll see in a moment, they succeeded at that. They evolved a passive dynamic walker. The second question they posed is, again, like the hybrid dynamic walker that we saw last time, can they then continue evolution but alter the environment in which the robot evolves? You'll notice in the second phase of evolution, the robot is now going to be evolved on flat ground, but they're starting with the passive dynamic walker. They're going to allow evolution to gradually incorporate neural control of this initially purely mechanical device. So they're only going to put a little bit, or evolution is only going to include a little bit of brain in this machine in the second phase of evolution. And fitness is to continue walking on flat ground. Okay, that's sort of the overview. So let's look at phase one, where they started by evolving passive dynamic walking. Here's the biped. You can see it's somewhat anthropomorphic. It's not that different from human legs. We've got feet, knees, and hips. And they've defined 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different parameters that can alter this basic architecture. Let's start with the masses here. So you'll notice there are 4 M's: MW, MT, MS, and MF. These are little, you can think of these little red blocks here as lead weights that they could place at different points on the hip or on the waist here. They could place it anywhere on the thigh. They could place the third weight anywhere on the shank or the lower leg, and the fourth mass they could place anywhere on the foot. You'll notice that whatever they do, whatever values they assign for these parameters on the left leg is reflected symmetrically on the right leg. One of the first lessons you learn in biomechanics is that if you want to move straight, it's a good idea to have a bilaterally symmetric body. The left side of your body should look the same as the right side of your body. Bilateral symmetry. Okay, so those are the masses. Then they evolved some other things like the leg segment length. So what was the actual length of the leg so they could have taller or shorter walkers. They also evolved the offsets of the masses. So you could see this mass here is actually placed quite a bit forward on the shank. It could be backwards. The weight could be placed a little bit inwards towards the center line of the robot, or outwards on the outer side of the shank. Same thing with the thigh weight. They evolved the length of the foot, the radius of the waist. This one is important. This is the angle at which the leg can rotate relative to the waist. So what is the stride length that this robot is capable of? The last thing that they evolved here is the starting hip angle around the y-axis. So if you imagine that this is by, this would be a by of 0, this would be a by of 45 degrees, 90 degrees, and so on. But this is only for, all these others are bilaterally symmetric. This is the one exception. So one of the legs is going to be rotated a little bit further forward, and the other leg, the gray leg, is going to start as the stance leg. You can imagine this makes sense if you have a declined plane and you put the passive dynamic walker on it. No matter how you build that mechanical device, if both feet are touching the ground and the robot is bilaterally symmetric, it's going to fall forward. So even in the case of our walking staircase and this little piece of paper, there are slight asymmetries that basically get this process going. They introduced B sub Y as this slight asymmetry. So the robot, when the robot starts on the declined plane, it's going to start with one of the feet slightly off the ground, but evolution can decide how much that foot should be off the ground. Okay. They then added in some springs. So you could relatively easily build this in PyroSim now. You can see all of the links here, all of the each pair of links that come into contact with one another. There's a rotational joint placed there. However, there's no motors. Remember, this is a purely mechanical device, but they did add springs, and you can see they have one spring that connects the hip to the shank, and then the pelvis to the shank. And then down here in the foot, they have another one on the outside of the foot and the front side of the foot. Let's do the foot first. So this one, this particular spring here means that if the base of the foot is close to the shank or far from the shank, the spring is going to try and pull it back to about 90 degrees. The one on the outside is going to make sure it's going to minimize the yaw of the foot. So if the foot rotates too much outwards, the spring will pull it back, and if it twists or yaws too much in the other direction, it'll pull it back. So the springs are trying to keep the foot more or less at 90 degrees. Same thing with the springs up here. One other detail, you'll notice that there's two springs here and two springs down here. The foot and the shank are attached by not just one rotation, one joint. There is actually a second joint allowing it to yaw and pitch. And I'm missing one. What's the one I'm missing? Yaw, pitch, and roll. Yes, this is not possible. This is not possible in the ankle. I'm sorry, I just realized I misspoke. So the ankle is allowed to change in pitch, and it's allowed to change in roll. This is roll, but not yaw, which is this. So yaw, pitch, and roll are the ways of describing how things can rotate in 3 dimensions. Yaw, pitch, and roll. Okay. So we have 1, 2, 3, 4. We have 1, 2, 3, 4 springs, and the fifth one that's not shown here is there is another spring around the knee, which is causing the knee to stay at about 180 degrees. And any movement away from this, the spring will pull it back. So we have a total of 5 springs: 2 in the hip, 2 in the ankle, 1 in the knee, 5 on one leg, and 5 on the other. Each spring has 2 parameters associated with it. This is true of most springs. It has the springiness of the joint, known as the stiffness, and the damping coefficient of the spring as well. So let's have a look at spring stiffness and spring damping for a moment. You can see my 4 little cartoons down here. Let's imagine we have a spring where we set a high stiffness, and we also set a high damping. So in the simulator, and I think this exists in PyroSim as well, I'll have to go look up the documentation for this, but you can add a spring to your robot as well. That spring requires you to supply 2 floating point values, the stiffness and the damping. If those two floating point values are high, that means that spring is stiff. It's like the coils are made from thick steel. It is very hard to compress and very hard to extend the spring. So imagine this is time on the horizontal axis here. The vertical axis is going to represent the length of the spring. You'll see at the beginning of this little cartoon here, the length is positive. So I've stretched the spring away from its resting length. So the y equals 0 here in my little picture. This is not a length of 0 for the spring. This is the length of the resting length of the spring, right? If you play with springs and you leave it alone, that spring has a default length. That's the resting length. With most springs, you can pull or elongate the spring away from its resting length and push it or compress it below its resting length. Okay, so high stiffness means it will very quickly, stiffness means it will very quickly return to its resting length. If you manage to pull a thick steel spring away from its resting length and let go, it will immediately return to its resting length. Damping is how quickly this oscillation gets damped away, right? A spring is springing and it'll oscillate around its resting length. How long will it oscillate for? Let's look at this one down here, high stiffness. So it doesn't want to go very far away from its resting length. But if there's no damping, it will continue to oscillate around its resting length. Let's have a look at low stiffness, high damping. In low stiffness, it doesn't take a lot of force to pull a spring very far beyond its resting length. And it also does not take a lot of force to push it below its resting length. Very easy to get it to oscillate far from its resting length. With high damping, however, if we do pull it far from its resting length, it will very quickly come back to its resting length. So you can think about this as low stiffness is a spring that's made from very, very thin wire, right? Kind of like a slinky. Low damping, low stiffness, low damping. It's easy to pull and push on the spring, but and also because there's no damping, it will continue to bounce indefinitely. Actually, this is most like a slinky if you ever played with the slinky toy. So for each of these 5 springs, we can set these 2 values. So we have all of these parameters we just talked about and all of these parameters, and we're listing them. All of these parameters are going to be the same. Sorry, I'm having some problems here. There we go. Okay. All sets of these parameters are the same for one length, and they're the same value on the other side with the exception of b sub y. As you've probably guessed by now, we're going to take all of these parameters and put them in a vector. We're then going to create a population of different random vectors. We're going to take each random vector, pull the values, pull all the parameters out of that vector and use it to construct the biped in the simulator and watch how well, if at all, that particular biped walks down the declined plane. Assign a fitness to that vector, go to the second random vector, take all those values, use it to construct a second biped in the simulator, watch how far that biped walks down the declined plane, obtain a fitness, assign that to the second vector, and so on. How many elements are there in this vector? How many parameters are we evolving? If you have an idea, go ahead and just type the number into chat. I will go back and forth between these 2 slides so you can count things up. Logan says 20. Everybody agree with Logan? Anyone have any other numbers? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 12, 13, 14. 13, 14, 15, 16, 17, 18, 19, 20, 21. Very close. 21 parameters. Did I get that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 parameters in total. We have a vector with 22 numbers, and those 22 numbers are going to allow us to construct this robot. Sorry, I'm having some problems with my slide advancing today. I think I missed a slide here. Here's a better overview of the overall structure of the robot. Again, it's got 2 legs. We have 2 degrees of freedom in the hip. The 2 degrees, a degree of freedom for our purposes equals 1 rotational joint. So we have 2 rotational joints in the hip, 1 in the knee, and 2 in the ankle. And remember, we got 1 spring for each of these 5 rotational joints. Okay, so we have 22 parameters, and I mentioned that this is a purely mechanical device. That wasn't completely true. There is a continuous time neural network, a CTNN. You'll notice that we're missing the R. There are no recurrent connections here. Here, we're eventually going to use sensors and motors. We haven't got there yet. But what we are going to do is we're going to use this neural network in a moment. And we're going to include one additional neuron called a central pattern generator. So this is, again, something that we haven't seen yet. We mentioned the bias neuron last time. The bias neuron always emits a value of 1, and that bias neuron allows a robot to act even if all of its sensor values are at or near 0. A central pattern generator emits a pulse. So in this case, this Cpg neuron is going to have a value of 0 for most of the time, but at a regular interval, it's going to output a value of 1.0. So it is going to emit a pulse of signals into the hidden layer here, and then the hidden layer out to 1, 2, 3, 4, 5 motors at each of the 5 joints. Okay. Again, I mentioned we've got our passive dynamic walker that has no brain, but now I'm introducing a brain. Bear with me. We've got this one Cpg neuron. It turns out, as always, a lot of details of artificial neural networks are inspired by biological neural networks. Animals have central pattern generators as well. These aren't individual neurons, but they're small neural circuits that spontaneously emit a signal. This is the reason why when you cut off the head of a chicken, the chicken will continue running for quite a while without its head. Reptiles and mammals have central pattern generators distributed through our spinal cord. Most of the time when you are walking, you are not consciously controlling your walking. It is the central pattern generators in your spine that are controlling the oscillation of your leg muscles. And there is a very simple signal coming from the brain saying walk, 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 walk. That constant signal is being sent to your central pattern generators that turn that constant signal into an oscillatory signal. Flex the muscles in your thigh, flex the muscles in your thigh, flex the muscles in your thigh. Okay. What we're going to do with our passive dynamic walker is take the 22 numbers, use it to construct the biped, put the biped at the top of the declined plane. Then we are going to allow the central pattern generator to emit 1 pulse, and then we're going to muffle the Cpg. That 1 pulse is going to flow through the hidden layer and out to the 5 motors, and the 5 motors are going to give an instantaneous torque to the 5 joints, and then everything will shut off. So strictly speaking, this robot is almost already a hybrid walker. In the very first time step, it receives torque. But for the rest of its time moving down the decline plane, it is a purely mechanical device. Okay, let's talk a little bit. About the motors here. So you'll notice that all of the 5 motors have VEL at the end. What we've been talking about when we've been talking about motors so far, we take the value arriving at a motor and we interpret that as desired angle. That's position control. There's a desired position or a desired angle that we want the joint to get to. There is also a velocity control, which is that the motor interprets the incoming value as a desired velocity. So if the value is 0.3 arriving at a motor, that value means the motor should achieve 0.3 radians per second. Or it could be revolutions per second, RPM. Doesn't really matter. It's something per unit time step. In this particular case, they're using velocity control. Okay, we'll talk about the sensors. We'll talk about the sensors a little bit later. Any other questions before we move on? As I mentioned, there's quite a bit of moving pieces in this experiment. So far, so good? Okay. Okay, so this central pattern generator is emitting 1 pulse, but that pulse is being sent to 5 motors in what leg? At the moment, it's going to be sent to just one of the 2 legs. I don't remember even if they mention in the paper. It doesn't matter as long as it's always only 1 leg. So 1 leg gets energized and the other one is passive. Okay, for now. Let's have a look at the fitness function. The structure, the formal structure of the fitness function looks a little bit different from what we've seen before, but not too much. Let's start with F equals D. What is D? Well, D is simple. It's the distance that the biped travels as it moves down the declined plane. You'll notice that they multiply D by 5 other terms. We'll talk about what these terms are in a moment. Let's imagine that these terms weren't here. Let's imagine that you evolved these bipeds to move down the declined plane, and the fitness function was F equals D. What kind of behavior do you think you would get back? How would evolution evolve the bipeds to move down the declined plane? Hannah says rolling. Rolling or falling and kicking the legs and sliding headfirst down the declined plane. If the only thing you ask for is distance, there is nothing that says stay upright. Remember that one of the 4 features that animals and this robot is going to have to grapple with is stability, staying upright as you move down the declined plane. So all of these 5 terms, and you'll notice they're all being multiplied together, these are all penalty terms. If you fall forward, let's find the fall forward one. That's 1 over 1 plus z. No, it's not. It's actually x here. So you'll see 1 over 1 plus x, and x is hip rotation about the x-axis. And it's easier for me to do this in class, but I will demonstrate a few silly walks I will try and demonstrate a few silly walks for you. So if this is the x-axis pointing into the screen, then this is positive x, and this is negative x of the hip joint. So if this value becomes very positive or very negative, the robot is tipping very far forward or falling very far backwards. And a large positive or negative value of x causes this term to approach 0. And now that I'm looking at it, I notice that if x equals -1, this term becomes infinite and undefined. So now that I'm saying this, I think there's an error in the paper, or maybe I misinterpreted this. X should always be positive. So this should probably be magnitude of hip rotation away from x equals 0. So this is 0, this is very positive, and this is also very positive. So as the robot is moving down the declined plane, we would like x to stay as close to 0 as possible. 1 over 1 plus 0 is 1, but 1 over 1 plus a large value means this term is approaching 0. And no matter how fast the robot is moving, d times something close to 0 is something very close to 0, and the robot gets penalized. So a robot that walks down the declined plane using a silly walk where it walks like this is going to be penalized and thrown out of the population. Okay, let's see. So we also have hip rotation about the z-axis. So this would be a biped that walks down the declined plane by twisting its body greatly about its long axis as it walks. Hip rotation about the y-axis. Y is pointing forward or down the declined plane. So high values of y would be a robot that walks down the declined plane by twisting to the left and right as it does so. So that is also minimized. So all of these terms here, these are meant to minimize or penalize various forms of silly walks. We started this lecture by pointing out that there's almost an infinite way that a biped can walk. We're looking for anthropomorphic walking like a human being. Okay, there's another one here, 1 over 1 plus r. This is feet rotation about the z-axis, so they also don't want feet that are twisting about too much. The final one is 1 over 1 plus t, which is the one that we just talked about. Remember at the beginning, the CPG gives, the CPG in the neural network outputs, for the first moment in time, it outputs a non-zero value, and that is ultimately interpreted at the values arriving here as desired velocities, which are turned by the motors into torques. We are trying to minimize the amount of torque that those motors apply in the first time step of the simulation. We don't want the motors to give a huge kick to the robot. We want to try and find a robot where all it requires is a very small poke, a very light touch to get the robot to start exhibiting bipedal locomotion down the declined plane. Okay, so now we have our robot, we have a little bit of a neural network, and we have our fitness function, so we're ready to do evolution. So during passive dynamic walking, in this case during evolution, they evolved the body parameters that we just mentioned, the 22 body parameters, and they're also evolving the synaptic weights between the CPG and the motors. Right? So the CPG gives a little kick, and that kick arrives at the arrives at the hidden layer based on these arrows. We have to evolve these weights as well. And then we have to also evolve the weights that go from, there's arrows coming down here as well. So we're evaluating all of the weights between the hidden layer and the motor layer, and all of the weights for the synapses that are leaving the CPG. So we're evolving the brain a little bit, at least how the robot starts moving. Okay. During evaluation, during a single simulation, we put the robot at the top of the declined plane. We supply this one CPG pulse, then we turn off the network and evaluate how far the robot moves down the declined plane. Okay, I love this paper, but one of the drawbacks is it does not have any videos, which is a real shame. So you're going to have to create a mental image of an evolved walker that successfully exhibits passive dynamic walking down the declined plane. Didn't take them very long to evolve a walker that actually does this, and didn't require all the human effort that went into very carefully shaping the physical passive dynamic walker. Okay. All right. So there are two more phases in this experiment. So once they got passive dynamic walking, they didn't stop the evolutionary algorithm. They let the evolutionary algorithm continue running. But in the second phase, they made a few changes. The first change is, actually the thing they didn't change is they continued to evolve the synaptic weights. They continued to allow evolution to evolve the synaptic weights that connected the CPG to the hidden neurons and onward to the motor neurons. They continued to evolve the 22 body body parameters, but they added a seventh term to the fitness function. 1, 2, 3, 4, 5, 6. They added a seventh term, 1 over 1 plus v. 1 over 1 plus v has the same form as these 5 penalty terms. So even though we don't know what v is yet, we know that we're now trying to penalize v. We want v, which is going to be a positive value. We're going to want this value to be as close to 0 as possible. V is going to be the difference between a given biped walking down the declined plane and the same biped when it's put on flat ground and allowed to walk for the same amount of time in the simulator. So they're going to evaluate now each genome, each set of parameters, they're going to evaluate it twice. Once on the simulated declined plane and once on flat ground. And they're going to watch the velocities of the robot in these two environments, and they're going to take the distance or the difference between these velocity profiles. So what does a v of 0 tell us? If we have a biped that manages to achieve a v extremely close to 0, what does that mean? Right. So the robot is going to have more or less the same speed if it's walking on flat ground or on sloped ground, as George says. Exactly. Okay. Another thing they're going to change during evolution is they've just finished this first phase. They have a passive dynamic walker that walks down the declined plane. As evolution continues, actually, so if you take the passive dynamic walker from the declined plane, put it on flat ground, there's very little chance that it's going to exhibit anything anywhere near the walking that it exhibited on the declined plane. So V is probably going to be very high. So over the phase of this second second phase of evolution, they gradually, from one evolutionary generation to the next, they gradually decrease the slope of the declined plane. And that helped evolution to eventually decrease V. So we're still maximizing D. We still want the robot to walk quickly down the declined plane, and it should also walk quickly on flat ground, but it hasn't had much experience walking on flat ground because these bipeds are emerging from phase 1. So V is probably going to be pretty high. There's going to be relatively low fitness in the second phase. But by gradually lowering the declined plane, the robots are evolving the ability to handle both environments. Okay. During a single simulation, when the robot is on flat ground, they're going to record the time to first heel strike. What is first heel strike? We have the robot, and when it's on the declined plane or on flat ground, remember that it has 1 foot off the ground. We start the simulation and we start a stopwatch, and we watch how long it is until that heel strikes the ground, and we measure that time interval. And we're going to use that time interval on flat ground to set the frequency of the Cpg. So I'm going to back up to the Cpg now for a moment. The Cpg in phase 1 only ever emitted one non-zero value. Now in phase 2, it's going to emit a non-zero value at a certain frequency, and that frequency is the time it takes the robot, that particular biped's heel to strike the declined plane. So let's say it's 33 time steps. So in the very first time step, the Cpg sends a non-zero value to the right leg, which causes the right leg to move. The robot starts moving, and 33 time steps later, the right heel strikes the ground, and at that moment, the Cpg now sends a non-zero value into the left leg. At 66 time steps, the Cpg sends a signal to the right leg, 99 time steps to the left leg, back and forth. So the Cpg is sending values into the two legs at a certain frequency that's been determined by how the robot starts moving on the declined plane. When I say the CPG is sending values into the right leg or into the left leg, what do I mean by that? Inside the right leg is this neural network, and there is an identical copy of this network in the left leg. So we've got 5 motor neurons over here. Remember, we have 5 joints in the right leg and 5 joints in the left leg. We have the 5 motor neurons from one neural network controlling the right leg and 5 motor neurons from the same network controlling the left leg. So 2 identical copies of the neural network. We're evolving all these synaptic weights. The sets of synaptic weights in the right neural network are identical to the synaptic weights in the left neural network. In the same way that the structure of the body is the same on the left side and the right side, the structure of the neural network is the same in the right leg and the left leg. If we were to look inside your legs, you would find some complex neural circuitry descending through your leg as well. That circuitry is pretty much identical in your right leg as it is in your left leg. Again, one of the principles of biomechanics is if you want to move in a straight line, everything should be the same on both sides of the midline of the body. Okay, so we haven't talked about the sensors yet. There are no sensors yet. I was just going to put my hand over the slide, but that doesn't help you, does it? The neural network at the moment is only the CPG, the hidden neurons, and the motor neurons. We have 2 identical copies in the legs. Okay, so we have at the beginning of phase 2, we still have a population of genomes, and those genomes encode the 22 body parameters and also the sets of synaptic weights that connect the CPGs to the motor parameters. So we take in phase 2, we construct the body of the biped according to this first genome. Then we label all the synaptic weights in both legs according to that first genome. We watch how the robot walks down the decline plane. We have our stopwatch. We record how long it takes until first heel strike. We take that same biped, we put it on flat ground. And now the CPG is going to emit values into the 2 neural networks of the biped on flat ground according to the frequency of heel strike. And we're going to measure how far the robot moves on the declined plane. Okay, so this fitness function, you can notice that all of the terms have no subscripts underneath. You can just in your head paint a subscript I under D, T, X, Z, R, and Y. D sub 1 is the distance traveled by the robot on the declined plane, and D sub 2 is the distance traveled by the robot on flat ground. T sub 1 is the amount of torque required when the robot starts moving down the declined plane. And torque of 2 is how much torque is applied to the robot as it moves as a hybrid walker on flat ground, and so on. And we're summing up. We take the product of these 6 terms on the decline plane, and then we add that to the product of these 6 terms when the robot walks on the flat ground, and we multiply all of that by 1 over 1v. How differently did the robot move on the declined plane and the flat ground? So in words, we're obviously trying to maximize distance of travel down the declined plane, maximize distance of travel on flat ground, minimize difference in behavior in those 2 situations, and minimize the amount of silly walking in both cases. So far, so good? I realize it's a lot of details. There's a lot going on in this experiment. Okay. If there's no more questions, we're going to push on to the 3rd phase now. Like before, we're going to just continue evolving the body parameters and the synaptic weights that flow from the CPG to the motor neurons. But you'll notice that we're going to allow the robot to gradually modulate or modify the way it walks based on its sensors. So far, the robot has no sensors. It is simply blindly trying to walk down the declined plane or on flat ground. So how do we do phase 3? So in phase 3, during evolution, we're going to reconnect the sensors to the neural network with small connection weights. So let's go back to the neural network. So we're going to allow the we're going to add in all of these sensor neurons, and we're going to connect these sensor neurons to the hidden layer with synapses. But we're going to start by setting all of these weights from sensor to hidden to values near 0. Why do that during evolution rather than simply set them as random weights and allow evolution to evolve those weights in phase 3? Remember, we're continuing evolution from phase 2, so we already have evolved weights in here. We're snapping on the we're snapping on the sensors and connecting them into the brain with small random weights that are near 0. Why near 0? In phase 3, we're going to continue. Evolving, walking on the declined plane and the flat ground, but now the robot is able to modify that behavior, tune that behavior using its sensors. Logan says, so it doesn't compromise the progress that's already made. Exactly, right? We already have an evolved solution. And as we know, the passive dynamic walker is finicky. It has very low robustness. It only works in a very narrow range of environments, and that allows it to be very energy efficient. So we have to be very careful. We don't want to reach in with a sledgehammer and break what we already have. We're reaching in, or evolution is going to reach in with tweezers and make slight changes. Okay. So during evolution now, in phase 3, we've expanded the genome again. We have, in that genome, we have 22 numbers for the body. We have however many synaptic weights for the Cpg to motor layer connections. And we have an additional set of synaptic weights that connect the sensors to the hidden layers. What are the sensors? You'll notice a whole bunch of A's and F's. A's are angle sensors. Angle are proprioceptive. We've talked about that before. A new sensor we haven't seen before are force sensors. Remember that there are springs here. We can attach sensors to the springs, and those sensors are going to report the amount of force that's acting on the spring at that moment in time. When a spring is at its resting length, there's no force. But we need, during walking, there are going to be forces that are going to pull or push on the springs. And the F's, the force sensors, are going to record those amounts of forces. We have some rotation sensors as well. So how much is the robot rotating about its x-axis? How much is the robot rotating about its x-axis as it walks down the declined plane? Rotate y. How much is the robot's main body rotating about the y-axis as it walks down the declined plane? And how much is the robot rotating about the z-axis as it walks down the declined plane? So rot x, y, and z are picking up the amount of silly walking that's currently happening. Finally, there are a few acceleration sensors as well. Where are those? They should be in here somewhere. Acceleration X, Y, and Z. So how much is the body accelerating about the X, Y, and Z axes? Okay, so this robot is actually now quite aware. It's got a lot of different kind of information flowing in from lots of different kinds of sensors. From now on, we're going to talk about sensor modalities. So sensor modalities are the different modes or the different kinds of physical phenomena that are picked up by the robot. Generally speaking, we talk about humans as having 5 senses. Or 5 sensor modalities. Humans actually have many more than 5 sensor modalities. See, hear, taste, touch, and smell. What else? What else can you sense other than those 5? Remember our discussion, thinking about thinking is misleading. We often talk about humans having 5 senses or 5 sensor modalities. We have more. Orientation, absolutely. So our vestibular sense, right? If you spin about, you mix up the fluid in your inner ear canal, you fall over. Yep, orientation. This is often known as your vestibular sense, technically known as your vestibular sense. Pressure, okay? So we feel pressure kind of on the skin. So when people say touch is obviously inaccurate, but is often used to sort of capture everything you feel at the skin, like temperature, pressure, moisture. Velocity of other objects with respect to yourself, okay, maybe. But usually you pick that up by seeing the object moving relative to yourself. So that's still vision. We're talking about sensor modalities here. Different sense organs that you have beyond eyes, ears, nose, mouth, and skin. Vestibular sense is inner ear. That technically is your 6th sense. There are also interoceptive senses, things that you sense inside your body. How many of you had breakfast this morning? Hunger is an interoceptive sensation. Pain, nausea, these are all interoceptive sensation. When we talk about the human 5 senses, we're usually implicitly assuming that we're just thinking about the things that we sense from the outside world. But your inner world is just as complex as the outer world, and often it's much more important to you than what's going on in the outside world. Okay, so sense modalities. This robot has 4. It can sense angles, forces, rotations, and accelerations. Missy says, what's the difference between the angle and rotation sensors? So the rotation sensors are the derivative of the angles. So technically, if we only gave the robot angle sensors, and if it was useful for the robot to sense rotation, it should be able, in theory, to evolve weights that would differentiate the angles to compute in the inner layer rotations. Back when we were talking about neural networks, I mentioned that if we have enough hidden neurons and enough synaptic weights, you can actually get a neural network to compute any function. This was one of the exciting things about neural networks back in the 1980s. There was the discovery that you could actually encode any arbitrary function with a large enough neural network. So I think that's probably where Missy's question is coming from. So angle and rotation are almost sort of redundant. It's sort of the same information, just presented in a different form. The authors probably just had an intuition that rotation would be useful, so they just sort of gave it to the neural network. So evolution didn't have to go to the extra effort of computing rotation. Same thing with acceleration, now that we come to talk about it. Okay, any other questions? Okay. So where did we get to? Step 3. Okay, so what are we going to do in step 3 here? As I mentioned, we're going to reconnect the sensors to the neural network, small connection weights, evolve everything. And we're going to do evaluation, same as before. We're going to evaluate each biped on the declined plane and the flat ground. In phase 2, we were gradually lowering the declined plane. So when we enter phase 3, the declined plane is now almost flat. We've come a long way. We've come a long way from phase 1, where we were evolving on a declined plane. Remember that the CPG is emitting signals into the two legs at a certain frequency. And they've actually plotted this for one of the evolved bipeds. So on the horizontal axis here, we have time in time steps in a single simulation. So we're looking at evaluation, not evolution. We have the value of the motor output on the horizontal axis here. We'll notice that the two motors we're going to look at, the motor in the hip and the motor in the knee, have positive values. And the CPG, if you'll notice carefully, is firing every whatever that is, 30 time steps or so. So every 30 time steps, it's emitting a pulse, and we're looking at just one of the legs. So you'll notice there's a single hip neuron, a single hip motor, and a single knee motor. So you'll notice as when the CPG fires, at that time, both the hip and the knee begin to flex. So the hip is going to pull. When the touch sensor fires, it's not clear from this picture whether the motor at the hip is thrusting the leg forward, extending the leg, or applying a force to pull the leg backwards or flex the leg. Doesn't really matter for our purposes. You'll see that there's some interesting dynamics going on here. The knee, the value, the amount of force being applied to the knee drops back to 0 pretty quickly for half of the walking, for half of the cycle of a walking gait. So for half a step, the knee has returned to 0, and in the hip, not quite. So it takes a while to get back to 0 and then actually jumps back up again. So I mentioned when you are walking around at a leisurely pace, half the muscles in your leg are slack for half the time. You can see that in this evolved biped, that's true for the knee, but not quite true for the hip. So again, one of the interesting things about evolutionary robotics, sometimes the evolutionary algorithm rediscovers aspects of human behavior or animal behavior, and sometimes not quite, slight differences. Okay. So that's phase 3. As I mentioned, there's a lot in this experiment. They actually continued on to a 4th phase. In this 4th phase, they continued evolving for another 100 generations. But in this 4th phase, they added in wind. So now, as the robot is walking on flat ground, they apply very small, random external forces, and they attach them to the body. Remember that at heart, in a physics engine, at the lowest level of the physics engine is the equation F equals ma, and if we rearrange that, we get A equals force equals mass times acceleration. A equals F divided by m. We can arbitrarily add in whatever forces we want to the physics engine. Here they're adding external forces that are going to tap on the different parts that make up the robot's body. And they just continued evolving for forward walking. And at the end, they took the best evolved robot at the end of the 4th phase, and they played it back many times in increasingly windy conditions. You'll notice they don't have any units here, which is a shame, but you'll notice in a relatively light breeze, the robot does perfectly fine. But as the wind starts to pick up, the robot starts to totter a little bit and falls over after a few steps, and eventually in gale force winds it can't really walk at all. There's an interesting comment in this paper. When pushed too far to one side, the machine was observed to adjust its foot placement by stepping inward to regain balance. This paper was published in 2004, and Big Dog came out a couple years later. You might remember from the Big Dog video, there's a clip in which somebody comes and kicks the robot as hard as they possibly can, or the Big Dog walks on ice and its feet start to slip out from under it while it's carrying 325 pounds. And the The robot manages to recover its balance by altering the way that it moves. I'm not sure whether Boston Dynamics was inspired by this paper or not, but interesting to think about. Okay, so the only reason that this robot can recover from this external force is, again, because it's now using its sensors. It's able to detect that something has changed, and it seems to know what to do. These authors kept going into a fifth phase. They kept evolving the bipeds. Now they introduced mistakes when building the body. Most of what we've seen in this course so far have been simulated robots. When we move next week, when we start talking about challenges, and one of the big challenges in evolutionary robotics is ensuring that robots evolved in simulation, when built in reality, can reproduce that behavior. One of the problems with building a physical robot is that physical robot is going to have slightly different physical properties, or a lot of very different physical properties from the simulated robot. So what happens if the physical robot has a slightly different body than it did in simulation? Will its neural network be able to recover from that body change? This paper introduces an interesting idea, which is you can prepare for that eventuality by evolving controllers that are robust to mistakes during manufacture. So here's an example over here. Whatever the L or the leg length was, they built the biped twice, but they added a little bit of noise to L, meaning that when the robot was built, it was a little bit shorter or a little bit taller than L. They continued evolving through this fifth phase. At the end of the fifth phase, they extracted the genome that had the highest fitness. They used that genome to reconstruct the robot many, many times. And during reconstruction or during manufacture, they introduced more errors over time. So up to 7% manufacturing error, the robot was still able to move, it was still able to take 40 steps. Above that manufacturing error threshold, the robot started to take fewer and fewer steps. But even after 30% manufacturing error, this is huge, the robot is still taking 12 or 13 steps using this hybrid walking behavior. It's an extremely impressive result at the time. Okay. This is where the experiment ended. They didn't do any more evolution, but at this point they wanted to see in what other ways was this walker robust. They know it's robust to manufacturing error. Remember that the legs in this robot are being controlled by the Cpg. Well, they took this best robot from the end of phase 5, and they altered the frequency of the Cpg pulses. So they either sped up the frequency or slowed the frequency. If you look very carefully, you'll notice, if you look at the widths between the spikes in the Cpg here, you'll notice the widths decrease around here. So they've sped up the Cpg a little bit. And you'll notice that stride length, represented by the purple curves here, are shorter, meaning the robot is taking shorter steps. And then it's taking very short steps here, and then they start to elongate or decrease the frequency of the pulse, and the robot responds by taking longer strides. So this is kind of interesting, just to show that the robot is robust to something that it was never evolved to be robust to. The other interesting thing here is to notice again that the robot is able to respond to this unique difference. Okay, that's the end of passive dynamic walking. Any questions about that before we spend the last 10 minutes of lecture talking about modularity? Okay, so as I mentioned, we're switching now from the history of evolutionary robotics to its future. What are some of the big challenges that the field wrestles with? We're going to look at two sort of specific challenges in the field today and next Tuesday. And then we're going to spend quite a bit of time wrestling with reality, this issue about how do we cross the reality gap? How do we ensure that what we evolved in simulation transfers well to reality? And then in a couple weeks' time, we're going to talk about scalability. Everything we've seen so far is one graduate student creating an experiment, evolving some robots in simulation, maybe transferring them to reality. The grad student graduates, another grad student comes in, and keeps going. How do we scale up evolutionary robotics to hundreds and thousands of robots and hundreds of thousands of fitness functions being written or constructed by hundreds or thousands of people? That's what we'll talk about in lectures 21 and 22. Okay, let's start with modularity. Modularity is probably the most important design concept in engineering, software engineering, computer science, architecture, pretty much anything that humans build. We try to build things in a modular fashion. Why? Well, modularity is good for lots of different things. The easiest way I know to sum this up is that if you do build a modular system, it is relatively easy to change or remove a module and have little effect on its overall performance. If everything is connected to everything else and one part breaks or needs to be fixed, the entire thing is broken. Unfortunately, the history of this particular technology has led to more and more non-modular devices. Why are modern cell phones non-modular? If modularity is so fantastic, why, when your cell phone breaks, do you not take it to the store, they extract the broken part and put a fixed part back in? Cars work this way. Houses work this way. If something breaks, somebody goes in and fixes the broken part, and off you go. Not with this. So Sid points out perhaps an economic incentive, planned obsolescence. Matt says modular things are larger. So modularity most of the time is good, but non-modularity has one advantage, which is you can usually make it more efficient, smaller, and so on. In evolutionary robotics or evolutionary algorithms in general, if you allow evolution to evolve not just synaptic weights, but which neuron is connected to which other neuron, and you watch evolution, evolution will evolve a denser and denser and denser connectivity in the neural network. If you evolve it to the neural network to do something, it evolves to become more efficient at it, and by doing so, it makes the system less and less modular, which is good in the short term, but over evolutionary time, it becomes harder and harder for evolution to make improvements for the exact same reason that it's difficult or impossible for someone to go in and replace the broken part in your phone. Evolution has backed itself into a dead end. It's created something that got more efficient and less modular, but now it becomes increasingly difficult to find mutations where changing one or a few synaptic weights will make the neural network better, that will allow it to control the robot better, and so on and so forth. So the challenge here is how do we evolve, the real challenge we're going to talk about in this lecture is how do we evolve things that passively dynamically walk or whatever it is we want them to do, but that they also remain modular. This is actually a difficult thing to do. There's a number of papers about this. We're going to look at an old paper about this topic today and next week. But it is still an open problem. No one has, in my opinion, no one has a good solution to this problem. Maybe this is something you want to look at in your final project. Okay, so what is modularity? Again, there is a whole literature on trying to define what it is. For our purposes, we're going to use the intuitive definition, which is something that's modular means there's tight coupling within the module. So in the engine of a car, all the parts that make up an engine are very tightly coupled together. The engine is a module. The wheel is also a module. There's a lot of parts inside a modern wheel of a car. So there is dense connectivity within the parts of a wheel, but little to no connectivity between the motor and the wheel. The motor affects the wheel and vice versa, actually. But the connectivity, however you want to define that connectivity, is less. This concept is very important in object-oriented programming. For some of you in this course, this is the first time you've come up against object-oriented programming. I hope you've got a taste for why object-oriented programming is useful. I don't know how many lines of code your code base is now, but it's probably several hundred, at least several hundred lines of code. You are obviously making changes to your code base, and hopefully by using objects and classes, it's relatively easy for you to modify one part of your code, like the evolutionary algorithm, without disrupting another part of your code, like the simulation part. Okay, so this is why object-oriented programming exists. You create classes, and inside those classes, there may be a large number of methods, and those methods may call each other. You may have dense connectivity within function calls within an individual class or an instance of that class, an object. You have another class that also has a whole bunch of methods that call one another, but hopefully different classes only call each other through a very small subset of their methods. We keep the interface between those classes as simple and narrow as possible. If you had a whole bunch of classes and they were all calling each other's methods, you'd end up with spaghetti code. It would be very hard to know where anything is, and making one change in your code at one place will probably break things everywhere else. Okay. We've actually already in this course seen two different kinds of modularity. The easiest one to wrap your mind around is structural modularity, which is what we were just talking about. Dense connectivity within modules, but sparse connectivity between modules. If we think about neural networks, if we have n neurons, each neuron is connected to all the other n-1 neurons. And if we allow self-connections, it's also connected to itself. When we were looking at C-tier and Ns, we had exactly that connectivity pattern. We had full connectivity. That means if we have a C-tier and N with 10 neurons, and then 20 neurons, and then 100 neurons, as the number of neurons, or the number N is going up, the number of synapses is going up with N squared. That is not a very scalable solution. So we can introduce structural modularity, or we can allow evolution to add in structural modularity, where we can allow evolution to cut or remove synapses. And we can ask, does evolution produce neural circuits that have dense connectivity and sparse connectivity between them? In the field of neuroscience, there is a controversy that's been running for decades about whether the brain is wired up in a modular fashion or a dense fashion. Are there modules in the brain or not? We saw when we looked at the small humanoid that was shaking the block, we saw an example of what's known as functional modularity, which is if we look at a particular system and we look at the output, the system itself may be structurally non-modular. Everything may be connected up to everything else, but it's producing distinct functional modules. We can push, quote unquote, push that neural system to produce one pattern. And if we push it in another way, it will produce another discrete pattern. As we saw when we looked at that humanoid robot example, the nice thing about functional modularity is by tuning the weights in that network, we can increase the number of functional modules. We can increase the number of discrete patterns that system outputs. Okay, we are not going to talk, please ignore these red boxes for today. We don't need them. We're going to ignore functional modularity in this lecture and just focus on structural modularity. Okay, so given a task, we want to evolve a robot to do something. We, as the investigators, may look at the task and we may break that task down into several subtasks. We may come up with sub-fitness functions, grasp the object, lift the object, drop the object. That's 3 different modules, or 3 different sub-functions. We may construct a neural network controller for that robot that has 3 neural circuits. So 3 clusters of neurons that are tightly connected with synapses, but few, if no, synapses between those 3 neural circuits. Or we may, again, be lazy and step back and allow the evolutionary algorithm to create modules on its own that are appropriate for the task. Why would we want to do this latter thing? Well, first of all, it's probably easier for us than having to sit down and formulate these subfunctions. It also turns out, which we're going to see in this lecture, that what we think are good ways to carve up a function into subfunctions is very different from the way that evolution thinks a function should be carved up into subfunctions. Our belief about where the modules are in a task often don't line up with where the modules are according to the evolutionary algorithm. And we don't have time to see that today. We're going to finish here, but we'll see that this is yet another example of where thinking about thinking is misleading. You have a quiz due tonight. You're working on assignment 8. I wish you a good rest of your day. Have a good weekend, and we'll see you all back here Tuesday morning. Thanks, everyone. Bye-bye.